Intermediate level. Understanding how hardware works. Introduction. After learning the names of computer parts, such as the CPU, RAM, motherboard, storage, PSU, and input-output devices, the next step is understanding how these parts actually work together. At the intermediate level, hardware learning moves beyond simple identification. Now the goal is to understand how data moves inside a computer, how the CPU communicates with memory, how storage interacts with the system, how the motherboard connects everything, how power is delivered to components, how hardware performance is affected by design. A computer is not just a collection of separate parts. It is a coordinated system where every component plays a role in processing, storing, transferring, and displaying information. Understanding how hardware works helps learners troubleshoot more effectively, choose better components, understand performance bottlenecks, build and upgrade PCs more confidently, connect hardware knowledge with software behavior. This is the stage where learners begin to understand the internal operations of a computer system. What does understanding how hardware works mean? Understanding how hardware works means learning what happens inside a computer when you turn it on, open a file, run a program, or play a game. In simple terms, hardware understanding equals knowing how computer parts interact to perform tasks. Example concept. Power on means components initialize, means OS loads, means programs run. Instead of only knowing component names, you start understanding their roles in system operation. Why this level is important. A beginner may know that RAM stores temporary data and SSD stores files. An intermediate learner understands how the CPU uses RAM, why SSD speed affects loading, and how the motherboard enables communication. Example concept. CPU plus RAM plus storage plus motherboard plus power means working computer. This level is important because it builds the bridge between basic hardware knowledge, practical troubleshooting, performance understanding, advanced computer architecture concepts. Without this stage, hardware knowledge stays shallow. Computer as a working system. A computer works by taking input, processing it, storing data, and producing output. Example concept. Input means processing, means memory/storage, means output. For example, when you open a game, storage provides the game files, RAM temporarily holds needed data, CPU processes instructions, GPU renders graphics, monitor displays the result. All these operations happen together in a coordinated way. How the boot process works. When you press the power button, the computer begins a startup process called booting. Example concept. Power button, PSU supplies power. Motherboard starts components. BIOS UEFI checks hardware. Boot device detected. Operating system loads. This process includes the PSU supplying power the motherboard, activating components, BIOS UEFI, checking whether hardware is working, the storage device, loading the operating system into RAM, the CPU executing startup instructions. The computer becomes usable only after this sequence completes successfully. Role of the CPU in system operation. The CPU is the main processing unit of the computer. It performs calculations, logical decisions, and instruction execution. Example concept. Instruction received means processed by CPU, means result sent forward. The CPU follows a simple cycle. Fetch instruction, decode instruction, execute instruction, store result if needed. This is often called the fetch-decode-execute cycle. Fetch-decode-execute cycle. This cycle explains how the CPU handles instructions. Example concept. Fetch means decode, means execute, means repeat, fetch. The CPU retrieves an instruction from memory. Decode. The CPU interprets what the instruction means. Execute. The CPU performs the required action. Examples include arithmetic, calculation, moving data, comparing values, sending commands to another component. This cycle repeats millions or billions of times per second. How RAM works with the CPU. RAM stores data and instructions that are actively being used. The CPU depends on RAM because it is much faster than long-term storage. Example concept. Storage means RAM means CPU. For example, a program is stored on SSD. When opened, it is loaded into RAM. The CPU reads instructions from RAM. Results may be written back to RAM. If RAM is too small or too slow, system performance suffers. Why cache memory matters. Between the CPU and RAM, there is another fast memory layer called cache. Cache stores frequently used data, so the CPU can access it more quickly. Example concept. CPU cache means RAM means storage. Cache helps reduce delays because CPU is extremely fast. RAM is slower than CPU. Storage is much slower than RAM. Cache acts like a high-speed buffer between the CPU and main memory. How storage works in the system. Storage devices such as HDDs and SSDs keep data permanently, even when power is turned off. Example concept. Saved files means storage. Running program means RAM. Process task means CPU. Storage is used for operating system files, applications, games, documents, photos, and videos. When data is needed, it moves from storage to RAM, then the CPU works on it. This is why faster storage improves boot speed, file loading, application startup, game loading times. Motherboard as the communication center. The motherboard connects all major hardware components. It acts like the main platform through which parts communicate. Example concept. CPU, trough, motherboard, RAM storage, GPU ports. The motherboard provides CPU socket, RAM slots, storage connectors, expansion slots, power connections, input-output ports. It allows different components to work together as a single system. Buses and data transfer. Data moves inside a computer through communication pathways called buses. A bus is a path that carries data, addresses, or control signals. Example concept. Component A means bus means component B. Common types include data bus, address bus, control bus. These buses help components exchange information efficiently. For example, CPU requests data address. Bus identifies location. Data bus transfers the actual data. Control bus coordinates the operation. How the GPU works with the system. The GPU is responsible for graphics processing. It handles tasks related to image rendering, video playback, 3D graphics, game visuals, parallel processing workloads. Example concept. Game data means GPU renders frames, means monitor displays output. In many systems, CPU handles general instructions. GPU handles graphics-heavy parallel tasks. This division improves performance, especially in gaming, video editing, and AI workloads. Power delivery inside the computer. The PSU, power supply unit, converts wall electricity into usable DC power for the computer. Example concept. Wall power means PSU, means motherboard, CPU, GPU, drives. Different components require stable power at different voltages. The PSU delivers power through connectors to motherboard, CPU, GPU, storage devices, cooling systems. If power delivery is unstable, the system may fail to boot, restart unexpectedly, crash under heavy load, damage components over time, cooling and heat management. Hardware produces heat while operating. More performance usually means more power use and more heat. Example concept. Processing work means heat generated, means cooling removes heat. Cooling is necessary because excessive heat can cause performance, throttling, instability, shutdowns, shortened hardware lifespan. Cooling methods include air cooling with heat sinks and fans, case airflow liquid cooling in advanced systems. Temperature management is a key part of hardware operation. How input and output devices interact. Input devices send data into the system, while output devices present results. Example concept. Keyboard, mouse, means system processes input, means monitor, speaker, outputs result. For example, keyboard sends a key press. Motherboard CPU interpret the signal. Software responds. Monitor displays text on screen. This interaction shows how hardware and software work together continuously. Hardware and software relationship. Hardware cannot be fully useful without software, and software cannot run without hardware. Example concept. Software instructions means hardware execution. Examples. Operating system tells hardware what to do. Drivers help software communicate with hardware. Applications use CPU, RAM, storage, and GPU resources. Understanding hardware operation also helps explain why. Drivers matter. Software optimization matters. Some programs run better on stronger hardware. Performance bottlenecks. A computer's speed depends on how well components work together. A fast CPU alone does not guarantee a fast computer. Example concept. Weakest component means system bottleneck. Examples of bottlenecks. Slow HDD with a fast CPU, low RAM causing constant memory swapping, weak GPU in a gaming PC, poor cooling reducing CPU speed, insufficient PSU causing instability. Intermediate hardware learning helps identify these performance limits. Hardware communication example. Here is a simple example of what happens when opening a file. User clicks file. OS sends request. Storage reads data. Data moves into RAM. CPU processes instructions. Program opens. Display shown on monitor. This shows that even a simple task involves multiple components working together. Common intermediate concepts to learn. At this level, learners usually begin exploring these topics. Fetch, decode, execute cycle. Motherboard chipset basics, data buses, clock speed, cores and threads. Cache memory. RAM speed and latency. SSD interfaces like SATA and NVMe. PCIe basics, thermal throttling. Power efficiency, hardware bottlenecks. These topics explain why systems behave differently under different workloads. Advantages of understanding hardware internals. Learning how hardware works gives many benefits. Advantages include better troubleshooting ability, smarter upgrade decisions, improved understanding of performance, easier PC building and maintenance, stronger foundation for advanced computer architecture. Example concept. Hardware understanding means better decisions and better troubleshooting challenges at this level. Intermediate hardware learning can feel harder because now the learner must understand interaction, not just names. Challenges include too many components working at once, confusing technical terms, hard to visualize internal processes, differences between theory and real-world performance. Example concept. Many parts working together means more complexity. But once the system is viewed as a flow of power, data, and instructions, it becomes much easier to understand. Concepts learned at this level. Understanding how hardware works helps learners understand. COM. How computers start and boot. COM. How CPU, RAM, and storage interact. COM. How data moves through the system. COM. Why cooling and power matter. COM. How performance bottlenecks happen. COM. How hardware supports software execution. This level creates a strong base for advanced topics such as computer architecture, processor design, memory hierarchy, buses and interfaces, hardware optimization, simple definition. Intermediate hardware understanding. The stage of learning where you understand how computer components interact to process data, store information, deliver power, and run software. Final summary. Intermediate hardware learning is about understanding how the entire computer system works together. Instead of only identifying parts, learners study how the CPU processes instructions, how RAM supports active tasks, how storage provides data, how the motherboard connects components, how power is delivered, and how cooling protects performance. This level is essential because it connects basic hardware knowledge with real computer operation. Once you understand how hardware works internally, you can troubleshoot systems more effectively, build better PCs, and prepare for more advanced hardware and architecture topics.